Good afternoon, everyone. My name is Desmond Martin. I'm the Chief Learning Officer at NextWave STEM, and it is my pleasure to join with you today as we are in another one of our free webinar PD sessions, teaching 3D printing in a meaningful way. I'm so excited today to have you with us because this is an opportunity to think about this particular emerging technology in some ways that we might not have considered before. One thing that we hear from a lot of educators at NextWave STEM is that, okay, there was this push to invest in a 3D printer, and I've seen 3D printing in action. I think it's really cool, and people are telling me that this technology is the future. But I don't know anything about 3D printing myself. Very few of my students may have done any kind of 3D printing. And now we're in this age of COVID, and I've got this beautiful, perhaps multi-$1,000 machine sitting in my classroom gathering dust. What can we do with it? How can we make this real for my students if they may be in a hybrid scenario or a remote scenario? Well, I'm really excited to have you with us today while we talk about making this 3D printer, this experience for your students really meaningful, something that can be easily adopted by you, believe it or not, especially when we think about ways to integrate it into our learning management systems, especially Google Classroom. Just a few housekeeping notes before we begin. The first is for our Illinois educators. Today is a professional development hour. That means at the conclusion of today's webinar, you will be receiving an email with a couple of gifts from us. The first is the certificate for today's PD. That way you can turn that into Illinois State Board of Education, get your credit, and you're all set to go. The second thing you'll be receiving is a copy of the slide deck. I think this is great. I love it. I kind of put a little bit of time and crafted this to be workable for our webinar today, but we also want to make sure that it is a reference for you going forward. So that's free. You get these slides and you can mark up and make notes and really integrate this as you see fit. But the third is that we will be recording today's session and sharing that with all of you as well. This will live on our YouTube page, but will also live as a gift to you. Just in case you have to drop off or once again, you want to reference this later on, you'll have a copy for yourself. And another bit of housekeeping is that we are in webinar mode today. So while we won't be able to see your face or hear your voice, we will be able to interact with you via the chat. If you have any questions or just want to dig into the weeds a little bit more, or you want to interact with us as we go throughout the course of the webinar today, feel free to jump in the chat or the Q&A functionality, and we'll make sure to get your questions and concerns answered live on air. But with those few things being covered, we will go ahead and we will press right on forward. And a great place to begin is at the beginning, thinking about who we are at NextWave STEM. Just briefly, NextWave STEM believes that our children, our next generation of learners, are going to need to be some incredible problem solvers. There are absolutely massive issues that our world is dealing with right now. I know we hear the word unprecedented one more time, we'll probably lose a little bit of our sanity. But before there was a global pandemic, we had issues of climate change and food insecurity, and making sure that even citizens in the United States had access to clean drinking water. These are issues that we know will require massive technological and societal changes and solutions. And we think that our next generation of learners are really going to be the ones that get us there. But in order to get there, they have to have teachers. They have to have exposure to STEM. They need to thrive in environments in their schools and at home where they can feel that they belong in the sciences, learning about technology, engineering, and mathematics. They can't do that if they don't have teachers that can expose them to STEM, even at really early ages. So at NextWave STEM, we think it's critical to empower you as educators, making sure that you have the curricula, training, and equipment that's necessary to take a student who might be on the fence, might imagine themselves as being the next great engineer or solving some huge problems. We want to give you the tools so that they can go on and take those AP courses, go and enroll for those 4-year degrees, go and enroll in those technical trade schools, get into renewable energy and green solutions, learn more about 3D printing and solar panels or carbon recapture. Go out there and be excited to solve these big problems from a young age and really believe that they can do it. And we're here to encourage you as well as educators. If you don't think that you have the skill set to take your students there, believe you me, you are more skilled than you know. So we've got 3 goals for today's webinar. Got quite a bit to cover. So we're going to move a little bit quickly, but we're going to make sure that if you've got any questions that you want answered, we're going to give some time at the end as well, covering a couple of different topics. The first is that we want to learn how to manage students in 3D printing courses using Google Classroom and Tinkercad. We love Tinkercad here at NextWave STEM. They are an amazing tool to allow students to learn about the basics of 3D design and move into 3D printing. And with the integration into Google Classroom, that becomes something that's really workable for many of our educators, especially here in the Chicagoland area. The second thing that we want to do is examine ways to physically model 3D prints using some other media. We know that during this time of COVID, remote learning and hybrid learning is on the table, really the only thing on the table for many of our student populations. And that means that many of them won't have access to a 3D printer. That does not kill our 3D printing experience in the crib, however. Many of our students have access to other materials and resources that allow them to experience designing and prototyping. We want to explore that today as well. And then the third thing we want to do in today's session is to focus on ways to make physical printing actually available to our students. You may be surprised at the kind of options that we can logistically make available if we understand the 3D printing process and understand some third-party resources, but even our own ability using some first-party resources. So really excited to dig into these subjects today. I should say that I am excitable, and I'm excited for our webinar today. But when I get excited, sometimes I tend to speak a little bit quickly. If I start sprinting as we go during the course of the webinar today, just give me a heads up, we'll slow it down. I had no problem repeating anything because I love all of this stuff. So let's go. So I actually have, just right at the very top, a little bit of crowd participation. I'd love to hear your answer in the chat here. Really simple question. You might think a little bit more deeply about it than you have to, but I'd love to get your answers here. What do a Honda Civic, a Mercedes E-Class, and a monster truck have in common? I'm gonna be silent for the next minute while you contemplate and put that in the chat. And there, I promise you, there is a reason I'm asking this question. So I would love to know, what do a Honda Civic, Mercedes E-Class, and a monster truck have in common? And I'll retype this question as well. No takers so far. Oh, Patrick with a good answer here. 4 wheels, a motor moves forward and backwards at high speeds and carries passengers. High speeds are relative, but I agree. When you think about human locomotion, yes, very high speeds. Great answer. Well, that's been a minute. So, Pat, love your answer there. All of these vehicles are what we would consider automobiles. They're cars. They're very different kinds of cars at very different price points and very different purposes even. That Honda says something a little bit different about your daily life than the Mercedes would. And that monster truck says very different, something very different about the life that you're living at the time that you might be driving that monster truck. But they all have some really common parts and pieces. They all have 4 wheels. They all have steering wheels. They all have some kind of internal combustion engine. They all have fuel that goes inside. And at the very end of the day, because they are automobiles, because they are transportation, they get people from point A to point B. The reason why I bring this analogy up right away is that 3D printing in very many ways is the same. When we work in 3D printing, all 3D printers, no matter what model, no matter what size, no matter what brand, no matter what price you pay for it, will always involve you going through 3 processes or some variation of these processes. You will always have to design the object that's being printed. You will always have to slice the object that's being printed. When we say slice, we're talking about that process of translating the raw design into instructions that your 3D printer can understand. And then you will always have to physically print your object. You might use slightly different material. Your printer may be bigger or smaller, may be able to print in different colors, maybe different shapes, may use slightly different motor technologies or different geometries. But these 3 steps always hold true. You will have to design an object to be printed. Design can also be download. Somebody has to design an object that has to be printed. That object will always need to be sliced for the specific printer and the specific settings for that printer to be printed. And then the object has to be printed. And the great thing about 3D printing is that we can make these steps available for our students, both in person and remote. This is engaging in this integrated field of additive manufacturing and design that allows our students who have access to machines as simple as Chromebooks to really dig into these 3 steps of our processes. So we'll consider meaningful 3D printing instruction from the perspective of our 3 steps of these process. So design, let's start there. How do we design objects? How do our students design objects that they're able to use, that they're able to print, that are going to be great examples for actually engaging with the engineering design process and additive manufacturing? Where's the first place to start? Well, a great place to start is really getting into the flow with Tinkercad. Really powerful tool. You'll see me doing just a little bit of tab flipping from this point out during the course of our webinar as we get more familiar with Tinkercad and some of our other tools. So a wonderful place to start is really getting your class prepped inside of Tinkercad. That means creating your own Tinkercad account and then creating classes. Now, the amazing thing about Tinkercad also is that it integrates with Google Classroom. When you create a new class inside of Tinkercad with your credentials, with your school credentials, that means that you also have the ability to have your students nested underneath that class using their school credentials inside of Tinkercad. Let's take a look at what that looks like right now. So I'm going to just quickly jump over into Tinkercad. It's going to load up. And what I'm looking at right now is a very simple, quote unquote, design that we have available to us in Tinkercad, but I'm not so focused on this right now. I'm going to click on our Tinkercad icon and go up to our dashboard. If you are an educator working with Tinkercad, this Tinkercad dashboard is going to be your best friend, where you have access to all of your designs, but also the ability to manage classes inside of Tinkercad by clicking on this class tab. So today we are doing a webinar and I have a webinar example. I can click on this webinar example and you'll see I have a list of students that I can add. I can add students manually by clicking on the Add Students button and inserting a name. Let's say in this case, Johnny. And when I insert Johnny's name, Johnny also gets a nickname. That was going to be really, really useful later on when Johnny needs to log in and register underneath my class. But I can also, at any time, copy and paste a list of students. So this makes my life really, really easy. If I've got a class roster, students that I know I need to add very quickly. and I can add multiple students at once. So I've got a roster of students, bunch of different students, all of my favorite young learners that may be in my class. And they have the ability to log in two ways. The first is to actually use a class code. If students are working in Tinkercad and have multiple classes that they might need to join, or just have their own Tinkercad account that's not associated with their school account, no problem at all. We can keep their lives really simple by giving them a link, tinkercad.com/join class. Then they'll enter their class code, this big one up here in green letters, and then enter that nickname from before. They're nested underneath your class. But for our teachers, but for our tinkerers, our students who are logging in with their school credentials, this is their first time working in Tinkercad, it's much, much easier just to copy and paste this link that's got a class code already included, enter their nickname, and they're ready to go. No having to go through the processes of verifying an email address, none of the stuff that gets us stuck the first time we use a piece of technology. The students are nested underneath our class and they're ready to go. So once our students are created, we want to integrate with Google Classroom. How does this become really, really useful for us going forward? Let's jump over to Google Classroom and give it a look. The most useful feature that your students are going to be working through is their ability to interact with the Google Classroom class drive. When you work in 3D printing, you're going to be generating a file called an STL, stereolithography file. Just means something that we're looking at from two different perspectives and what allows you to see an object in 3 dimensions. Inside of Google Classroom, a tool that many of us are already familiar with, I've created a little sample class, and we should already really well know how to set up our classwork. Different tasks that become really useful for us in the classroom, whether that is asking a particular question for our students. In this case, so what materials can we use to print from our 3D printer? We can also create just specific assignments. In this case, it may be a sketch, something that they may use in Google Draw, or a specific task inside of Tinkercad, where I would like them to grab a cube and then actually pull it into their workspace. From there, our students would actually rotate back into their Tinkercad accounts. So they're kind of using these tools in conjunction with one another. And in this case, they would create a new design. But instead of creating a new design, I'm going to tinker the design that I've set up for today's session. So students inside of Tinkercad are able to design. And if it were my first assignment where I need them to pull a box into the workspace, easily add shapes inside of Tinkercad with no problem. This would satisfy what I would need them to do in terms of the first assignment. And once they satisfy that assignment, what our students would need to do is save their work. Clicking on this export and save as an STL. That's going to become really, really useful later on. So right now, Tinkercad is working in saving this file. This STL file format is super powerful because it captures all of the 3-dimensional vertices, all of the different geometries, all of the different polygons that actually make up this 3-dimensional shape that students may have designed or downloaded. That's also going to become useful because that's going to be the actual meat and potatoes of the lesson, of the student work that they're turning in for us to evaluate later on. So as they're downloading those files, they will actually be re-uploading them into our Google Class folder. Many of us don't even know this, but Google Drive supports a number of different file formats, including STLs. So in this case, my sample 3D printing class has downloaded a number of different file formats. Their particular project here was really focused on a new kind of cell phone charger that they're designing. And when we click on our cell phone charger, we have the option to use third-party software to actually view the objects they've designed in the cloud. That becomes a really, really useful tool for us as educators to understand what our students are designing and how they're designing before we ever get to the phase where we're worried about the 3D printer. So right away, Google Classroom G Suite gives us the tools to not only design and integrate students' work right into our Google Drive, but also to inspect and know what our students are doing as they're working through their design processes. That is a really, really powerful integration that we want to make sure that we take advantage of, especially if Google Drive is our primary learning management system, which for many of us, it is. So after we get in the hang of actually modifying our Google Drive and setting it up in such a way that our students understand the expectations like they would in any other of their Google Classroom classes, we continue to build our skills as educators. If I've never done 3D printing before, it's useful for me to actually get a few lessons and experiment with using Tinkercad to build my 3D design repertoire. How can I do this? First and foremost is understanding that our 3D design software isn't just out there sitting and saying, okay, do the best you can. There are plenty of free resources for us to learn design. The first is actually inside of Tinkercad. There's a whole lesson section that we're able to engage with to teach us some of the basics of using Tinkercad. But there are also classes in Instructables, and NextWave STEM has a free resources section for you as well, including the curricular material that we integrate with our classes. These are all really good resources to learn and build our own skill with respect to 3D printing. So now we're in this space where we set up our Google Classroom, we're ready to go there, our students are ready to go there. We set up our own skills. We're able to navigate Tinkercad, we're able to move around and actually do some decent designing of our own. Now the question becomes, okay, how do we help our students move beyond just the 3D printing component of design and modeling? This is extremely important because we've got our 3 steps. We've got designing, slicing, and printing, but we know that our students might not have the opportunity to actually use a 3D printer at home. How can we help our students move beyond that limitation? Well, the first is that we want to just expand our ideas for how we can visualize design. The first is really to understand the connections that Tinkercad makes for us natively inside of Tinkercad. There are some awesome tools that will allow us to visualize and prototype beyond what we just see. So flipping back in the Tinkercad, I have this lunar module that has been lovingly 3D scanned from the Smithsonian Institution in Washington, D.C. Many of our students won't be able to make that field trip this year because of the nature of the virus. However, we're able to mock it up and modify it and actually see this thing in a surprisingly tactile way. But maybe, just maybe, our students are huge fans of Legos. Maybe they're such huge fans of Legos that they have an extensive Lego collection that they may be working with at home. Well, Tinkercad has the ability not only to mock up in standard 3-dimensional space, but clicking on this tab that says Brick, Tinkercad then flips the design that we've laid out 3-dimensionally and renders it in the highest fidelity that it can in Lego bricks. So if our students have a few dozen Lego bricks, for example, they can actually mock up and see how that design will look in Lego. And if they have those bricks at home to work with, they can actually practice building their designs out of those Lego bricks. Now, another really useful feature inside of Tinkercad is the fact that it just doesn't give us a mess of Legos that are put together in a jumbled group. Instead, if we click on the Layers tab, it also defines each layer of Legos. In this case, there's 11 of them. And clicking up and down in this arrow gives us the ability to build in more and more Legos and see where each layer needs to be. Very, very similar to what we would do in 3D printing in order to build this model. And we can go and do that at different levels of detail. So if I go 2x, I get, after a little bit of math, a little bit more detail with many more layers. Well, how many layers exactly? In this case, 21, so we double our layers. Or we can triple our original amount of layers to 30 layers of Lego bricks, going in finer detail and getting higher fidelity when it comes to our models. This is a great way for our students to design and then construct if they don't have access to the 3D printer, but have access to a physical tactile tool like Legos. Many of our students do. And this actually becomes a great learning experience for them. But let's say our students don't have access to a mess of Legos. Legos are really fun. Students collect them throughout their lives, but maybe some of our students never got into Legos. How are they able to mock up and model with a 3D design? Well, if they don't have access to Legos, many of our students are electronic gamers, love gaming, and love a game called Minecraft. Clicking on this Blocks tab allows us to take that original 3D design that we rendered inside of Tinkercad and translate that into Minecraft blocks. This is amazing because with the educator edition of Minecraft available to our students don't need anything except their computers, their actual devices, and not even an internet connection to go inside of Minecraft and reconstruct the designs that they have built. In very much the same ways that they might with Legos. 1 degree of fidelity, then the 2nd degree of fidelity, and then this 3rd high fidelity model that looks much more like the original model that we had. So we've got options for our students. 3D printing in Tinkercad allows us to expand a little bit outside of our normal comfort zone when we think about using 3D printing and 3D design software just for the purposes of 3D printing. We can still keep our students engaged. Useful shape categories like the Making at Home collection or the Oregon Museum of Science and Industry collection. Other types of objects that we can pull into Tinkercad like circuits and components. Objects that are completely 3D printable right from the Tinkercad library. These things allow us to generate STL files that we can modify and use inside of our Google Classroom. So now that we've talked a little bit about ways to expand beyond just using the 3D printer, we want to talk about, okay, got the classroom set up, got the actual design portion set up, even have a student options for my students who are distance learning and don't have access to a 3D printer, I should say. How can we effectively use an instructional model that moves us towards towards slicing and printing away from design? Because so far everything that we've done focuses on the digital design. How can we move towards slicing and printing? Well, the first thing that's useful to understand is that at NextWave STEM, we really do believe in the 5E instructional model. Many of us are really familiar with engage, explore, explain, elaborate, and evaluate. That's a tried and true formula, and we continue to embrace that at NextWave STEM as we make sure that our students have the opportunity to explore this new technology. What does that look like in a hybrid or remote scenario with instruction, however. Many of us have been working hard to adapt our learning models to the hybrid structure, and in NextWave STEM, we've done the same thing. We believe that teaching 3D printing, making it meaningful for our students means that we want our students to engage with real world problems that they need to solve. So we start with that, asking that question, what's a real world problem that we can solve using 3D printing? From there, we want to explore that question through group collaboration. That can be in a chat, that can be in breakout rooms inside of Zoom or inside of Google Meet, but also working with the instructors. From there, we have this small group exploration that allows us to dig in deeper, especially when we think about the engineering design process and where we need to prototype. Instruction, when we think about using three-dimensional design tools or slicers or thinking about settings, and students are following along and taking notes, but also experimenting on their own and with their designs and their slices. That becomes really, really powerful as we're explaining more about how the technology works. And there's actually this really a beautiful opportunity for students to elaborate on their learning with the independent work that they're able to do. These are the designs that are getting uploaded into the Google Classroom or whatever your LMS of choice may be. From here, we're transitioning from prototyping with Legos or Minecraft bricks, and we are really including those options for hybrid and remote. But after we've done that work, we are now going to move into this evaluation phase. How good is this design? Does it satisfy what we want to have happen? Can we modify this design in our next lesson to get closer to what our goals are? So this is our second audience interaction moment. A great place to begin, and we think about this as we explore, is thinking of a real world application, a real world problem that we want to solve with a 3D printer. We can rip an answer right from the headlines here. What is something that is a real world problem that students have been using 3D printers to solve? This is this place where this is the engagement moment. Can you think of something that students have been doing with 3D printers in the last 8 or so months to help solve some real world problems? And I'll take another 45 seconds for us to throw an answer in the chat there. The answer might seem a little bit obvious. We see these solutions kind of pop up in the news cycle every few weeks or few months or so. Maybe some of our own students have participated. When we think about students using 3D printers to solve real world problems, we really think about what's happening around us and what they have access to. Students have been practicing citizen engineering to actually design all kinds of different solutions. Lead filtration devices for homes that are dealing with lead poisoning, with issues of drinkable water. But more even urgent, perhaps, is this idea of producing personal protective equipment, PPE, for COVID-19. Things like face shields and masks and respirators and even assistive touch devices. Our students have been using 3D printers to actually solve these problems, making and designing for vulnerable populations, for first line responders. Our students are able to engage with a real problem. As we move through an instructional model, we understand that collaboration becomes key. So as they're designing, they're not just working in the design inside of Tinkercad, but they're also using the technologies that allow them to meet in class like Zoom or Google Meet. They're also using expanded actual collaboration tools. When we think of G Suite, Jamboard has been added to our Google Meet space for many of us, or they may even be using specialist drawing and markup technologies. When we think about AWW or ChemDraw for our advanced science students, or LaTeX, those who are publishing scholarly articles. These things become available for us, for our students to actually work together collaboratively. And document collaboration, like I just mentioned, is really key to that. If we are writing up our brief and we want to understand our constraints, having 4 different documents and working in that document doesn't make as much sense as working together as a group. So we get at this point now where we're collaborating, we have our tools, we have our design tools, but now we want to actually focus on the printer. Slicing is this intermediate step where we have the design that's been done in raw math, and now we have this printer that's ready to take in this design, but we have to give the printer instructions. We have to tell the printer how long it should take, how thick the layers should be, how much material, what kind of patterns and what kind of geometries the material will actually be constructed out of, whether or not this material is going to be completely solid or completely hollow or somewhere in between. Our students have to translate via slicing. So this becomes really, really useful when we think about collaboration because our slicing files, those instructions for the machine, can also live inside of our learning management system, in this case, Google Classroom or Blackboard or Canvas or any other learning management system as well. But slicing becomes super important for us because it is the actual machine-man interface between the 3D printer and the design. Just like we've loaded up our STLs and be able to view our files, we're able to load up our slices and we're able to now explore this idea of computer-aided manufacturing with a little bit more detail. So when we're thinking about slicing, we're actually digging into this world of computer-aided manufacturing. The slicing software, all it's doing is taking that 3D file and translating that file into a set of instructions called the G code. No matter what 3D printer you're going to use, you're going to be producing that G code that gives instructions on which kind of extra structures to build to make sure your 3D print doesn't fall down, the temperature that it should be coming out of, and the actual orientation and what material you're using with the printer. The analogy I would use is that if you're driving your Mercedes and you know that car takes premium gas, this is the instructions to make sure your car gives premium gas and uses that gas effectively. If you're driving that monster truck and you know that monster truck requires race fuel, these are the instructions to make sure that the machine is getting what it needs, and that way you're getting the best results. Different kinds of slicers, all of them are open source and all of them are free. They usually come bundled in with your 3D printer. Slicer, MakerBot is a big brand name. They have a slicing software called MakerBot Print. Cura is completely open source, and then we have AstroPrint, which we love and use in our courses because it's open source. It ensures that our students are able to slice no matter where they're at. They don't have to download software. If they have a Chromebook, they are able to slice and prepare a actual 3D printing file to come off of the printer. And just like I mentioned, we are working with a slicer. In this case, it's AstroPrint. We're changing those different things. We're making those slight changes that can really affect the effectiveness of the printer. We are making decisions, things like scaffolding. If we've got a 3D print, an object that might be shaped like a T, for example, a skinny tower and then some arms sticking off from the side. If we understand how 3D printing works, we know that once we get to the top of that T where those arms are sticking off the side, just like if we were building a building, if we don't have some kind of support structure, those arms, they're actually gonna fall down. They won't even print. We'll end up with a spaghetti mess where our 3D object should have been. And this actually allows us to make sure that we're printing our object, no matter the geometry, in a way that's going to give us a successful print. But then we have to consider this idea of plate adhesion. What happens if, as we're printing our object, it actually slides at the bottom of the 3D printer? The 3D printer we can think of as a robotic hot glue gun. It's shooting out material from an arm at about 200 degrees Celsius. And that material is sticky, it's hot, it has the ability to impart some force on our 3D printed object as it's being printed. It can pull, it can shift, it can cause the 3D object to pull up from the place where it started printing. And if it does, our 3D printers aren't smart enough to recognize that the object is shifted. The 3D printer will continue to print on with the instructions that has been given, and then we get a spaghetti yarn ball of a mess. Plate adhesion, making the decision about how much material is actually at the bottom of the 3D print becomes important. And then we have this idea of fill density. How much stuff is on the inside of the 3D print? Is it going to be completely hollow? Is it going to be completely solid? Are we okay with this print being really easily crushable if it has a really, really big surface area and a really, really low density? Do we want our prints to come off a little bit faster? The trade-off between weight and strength and how much time it takes to produce an object is something that our students will really have to consider when they think about the engineering design process. So AstroPrint allows our students to consider all these things as they're building, as they're prototyping, as they're actually preparing to produce their 3D printed object. So our students have designed, they've downloaded, they've modified, they've adjusted, they've come to an object that they're ready to print. And they've collaborated with their teammates going through the engineering design process to do this. Everything's living in Google Drive and we're happy. We've gotten them to this place where it's time now to slice. They know the printer that they're using, they've considered the slicing options, they know how much time and how much material it's gonna take. They've done the math and they know exactly how much this print is actually gonna cost. So we can do some cost benefit analysis for this object that we are about to print. But now here comes the tough part for us, right? In the time of COVID, we have to answer this question: how will you ever get this print? Who's going to print it? If you don't have a 3D printer at home and you can't get access to one at our school, or you might have limited access to one at our school, how are we going to get you this object? How are we going to actually close this engineering loop where you get this object and you can actually test its efficacy? Well, there are a couple of different options, and they're mostly logistical in nature. One makes a whole lot of sense and one you might be surprised about. Now, the first, for a hybrid situation, is that we would actually take charge of that 3D printing experience for our students. They're handling the design phase, they're handling the slicing phase, but because they can't get physical with the printer, that means that you become the one who manages the printing process. And that may seem time consuming, but the great thing about a printer is that a 3D printer is that we can think of it just like we would our normal inkjet document printers. Very few of us, if we need to copy many documents, would just sit there and watch the copy machine go. We set up a copy machine with some instructions, we go on and do something that actually brings value to our days and brings values to our students' days. And then we walk away and come back when our prints are ready. We can do the same thing with our 3D printer. I get the question all the time, how long does 3D printing take? And the answer really is, it depends on how big the objects are, how many you're printing at the same time, the settings that are used. It could be as short as 30 minutes for an object. It can be as long as 12 hours for a batch of objects. But that's the thing that we understand, is that we don't have to be hands-on with the printer. So if we manage our time, if we understand the concepts of batch printing, knowing that I can print multiple objects at once and then come back overnight, or come back after lunch period, or come back at the end of the day. If we take advantage of the opportunity to detail that process for our students by recording the printing process in place for their specific objects, if we get a sense of the order of operations, knowing when we can remove objects and start up the next print, we can print for an entire class of students in relatively short order. This doesn't become something that we have to be scared of. We just have to get our ducks in a row and we'll be able to do reasonable 3D printing for our students at the school. Or if we're in a hybrid situation, giving our students a chance to set those things up and prepare them for that in-school time that they have with us in our 3D printing course. But the second option that might be a little bit more surprising is the fact that this 3D printing industry is exactly that. It's an industry. There are hundreds and thousands of different 3D printing professionals who do commercial 3D printing. that will take an STL file that is shared with them straight to their website and will produce that high fidelity 3D print for you. For our students who may be remote and have no chance of getting access to the 3D printer, this can make all the difference. To know that their STL can be uploaded to a site directly from Tinkercad and then produced and shipped back to them. This allows us to close that loop where there's a missing cycle. This allows them to get that 3D printer object and test it. This allows them to actually define those settings just as we had in our slicer and make sure that our object is in high fidelity and at a relatively low price. Sites like TreatStock, iMaterialize, and many, many more are really useful to make that happen. And it really just depends on your specific instructional scenario. This is a model that we use a couple of times. It helps us wrap our heads around the situations we may find ourselves in. There are a couple of different scenarios depending on the grade, the actual learning needs of students, but across the country, they break down into 3. We think of them as the surge of infections, where we are in a learn at home scenario and then have to go remote. We think about it as a not ready to return, where we were learning at home, and then we might eventually make that change back to going back and learning in school. That's something that we all hope for, but that's the situation where we find ourselves in, many of us right now. And then there's the hybrid instructional model, where we might have different school populations, an A band and a B band, spending some time learning at school, some time at home, and then flipping back to school, just keeping those exposure events as low as possible. Our 3 phases can live in these different places, depending on which model we find ourselves in. If we are at a surge in infection scenario where we're doing learning in our school and then we have to make a change to remote learning, designing and slicing can work in person, synchronously in school. And then when we want to close that loop, we're able to do print delivery while our students are at home. They still get their objects, or you print them at the school and those are things that are dropped off or picked up. If we are in our not ready to return scenario where we're learning at home still, we can design and slice in the cloud using Tinkercad and using AstroPrint at home. And then once our students are back in school, they have that ability to make that quick pivot to using your 3D printer. We dust it off, we make sure it's ready to go. We've got plenty of filament, and our students hit the ground running because they've done all the design work ahead of time. Or if we find ourselves in that hybrid scenario, we can design at school that one-to-one good attention that students receive with you as their instructor. At home, they're doing things like slicing, continue to ideate, refining those designs. And then when they get back to school, everything's prepared and ready to go. The great thing about 3D printing is with the options we'll be showing you today, we've shown you that no matter your instructional situation, no matter your circumstance right now, 3D printing can be done in a way that really becomes meaningful for your students and meaningful for you, empowering you not to only understand one part of this process, but the entirety of the process. So that was a fire hose of information. Lots of stuff there that we need to consider, we need to break down, and we'll find those considerations and those help, when you use NextWave STEM's courses and materials. What else can we do to help you at NextWave STEM? Well, the first is something that you're already doing. Our free webinar series is continuing. Generally, each Tuesday at 4 o'clock Central Time, you'll join me, one of my colleagues, or even a special guest as we talk about ways in which you can make STEM more relevant, more powerful for your students, especially during this time of COVID. But the second thing that we're also doing is actual live instruction. Talk with us at NextWave STEM. We've got a roster of certified trained instructors in all of our courses. We're able to do instruction where we send equipment out to you and your school, so your students can be one-to-one on their equipment from home or at school as we're doing remote instruction. or we can do remote options completely, where students are able to simulate the technologies as we work through our course material. And then, of course, because our goal is to support you as students, as teachers, I should say, and teachers who are lifelong students, it's important for us to make sure that you're empowered. That means giving you curricula that you can use on your terms, on your time frame, with your students that you know and love. NextWave STEM curricula, we offer an all-in-one solution where you have access to the curricula, where you have the equipment that you need, and you have training in each one of our courses. That way, you're not just renting NextWave STEM, you're owning NextWave STEM for yourselves, and you're empowering that next generation of learners, regardless of whether or not you're teaching in school or remotely. So it's been an awesome time. We've covered quite a lot of bit of information. I just want to take the second to pause for any questions that you might have about anything, about slicing, about designing, about printing, about NextWave STEM options, about integrating with Google Classroom. Any question that you have is a good question. And I will pause just for a few moments to make sure that as those fingers are going, we have the opportunity to answer you. And believe you me, as an educator, I believe that there is no such thing as a bad question. Questions may be a little better than others, but there's no such thing as a bad question. If you have a bad question or you think it's a bad question, that's actually a great question, or if you have a question that you know is a great question. I love questions. I love interacting with our educators. You can reach out to me at any time with any of your questions. That's my name. That's my face in black and white. If you look into the corner of your screen, you'll also see my face in color. I'm once again the Chief Learning Officer here at NextWave STEM. And my email is really, really simple, desmond@nextwavestem.com. You can also find NextWave STEM on all major social media platforms. We are on Twitter, we're on LinkedIn, we are on Instagram, and we're on Facebook as well. We're not on TikTok. I'm glad TikTok did not get banned. I'm a fan of free speech, but I neither tick nor do I talk. So that's something we might do in the future. But if you have any questions about anything or about the materials we're going to send you after the webinar today, feel free to reach out to me. I love getting into the weeds. Ladies and gentlemen, thank you so much for spending this time with us today, talking about how we can teach 3D printing in more meaningful ways, especially during this time of COVID. We're asking that you continue to be safe as we're moving towards a new year. And as we're moving towards this new year, we're hoping that you continue to find excitement and joy in teaching, and excitement and joy in teaching emerging technologies. We have another webinar next Tuesday at 4 p.m. We'd love to see you out. Until then, be safe, everyone, and we will talk to you soon. Bye-bye.